Recall that earlier in Chapter 3, we introduced the stress-strain diagram in the context of normal stress and normal strain. Those arise from a normal force or an axial force. Now we will briefly study the stress-strain diagram in the context of shear stress and shear strain, that is, the shear stress-strain diagram. The experiment used to gather data regarding shear stress and shear strain usually involves a specimen in the shape of a thin tube that is subjected to torsional loading, torsional moment. If measurements are made of the applied torque and resulting angle of twist, the data can be used to determine shear stress and shear strain using methods explained later on in Chapter 5. So from the data collected in the previously described torsional test, the shear stress-strain diagram can be constructed. So we have shear strain values plotted on the horizontal axis. Remember, gamma represents shear strain, as we learned in Chapter 2. And then on the vertical axis, we have the shear stress values represented as tau, tau representing shear stress, as we learned about in Chapter 1. Shown below is a shear stress strain diagram for a typical metal. Okay, so we usually see for most materials an initial linear region of the curve, and then something like this where it increases and then decreases here to some point of fracture. So let's define a few important parameters. We do see some similarities between this shear stress strain diagram and the normal stress strain diagram. For instance, as we said, the initial region very often is a nice linear function until some certain point, the proportional limit. So we have a linear relationship here. We'll call the slope of that line uppercase G. Okay, so that's the modulus of rigidity, aka the shear modulus. It would be analogous to the elastic modulus from the normal stress strain diagram. It's the slope of that initial line. So rise over run, G therefore would be tau over gamma, shear stress over shear strain. The proportional limit is tau sub PL, PL for proportional limit. That would be the point at which the curve becomes non-linear, so at that point there, where we have tau sub PL, the proportional limit corresponding to the shear stress, and gamma sub PL for the shear strain at that point. We also can define the ultimate shear stress, tau sub U, U for ultimate. That would be the maximum point, maximum stress, shear stress on the graph. And the fracture shear stress would be the stress at fracture, represented by this point here, tau sub F. And there is a relationship between these three important material parameters, E, G, and nu. Note that it is shown in Chapter 10 that the three material constants, E, the elastic modulus, G, the shear modulus, and nu, Poisson's ratio, are all related by the following equation, where we have uppercase G, the shear modulus, equals uppercase E, the elastic modulus, over 2 times 1 plus nu, Poisson's ratio. Therefore, if the values of two of these material constants are known, then the value of the third unknown constant can be directly calculated from the above equation.